Time we had a look at parallel transport to move one vector from one point to another one. We had an idea of our derivative operator. And as I said, one of the things that are intimately linked is the fact with curvature is that if you parallel transport a vector, you don't get it back to the same spot in a curved manifold. Whereas if you parallel transport a vector in a flat manifold, you always come back to the same spot. And so there must be a natural way to describe curvature as well as to describe its relationship to parallel transport. And where we've seen curvature before was also when we did the origami. Remember, we had curved surfaces over there, and that curvature we described simply by a 2-index tensor. And I said that this is a special case, okay? What we're going to do now is actually derive curvature and introduce a thing called a 4-index tensor, of which that 2-index tensor can be gotten from, but it is not the full description of curvature. Curvature always needs 4 indexes. Okay, and so basically what curvature is given a derivative operator, delta A, if we can parallel transport a vector from P to Q, along a curve C, and then we can actually start connecting the mismatch with the curvature itself. So let's suppose we start at a point VP, we start with a vector VP at P, and the vector at Q, P, we then get, and in general it's dependent on C. Okay, so in flat space it's not, it goes around and comes back the same. In general, the curve that you transported along determines what the vector is at Q. Okay, so you can have, for example, if you were to take a curve around a sphere, you could take one curve and transport it right back to the equator, and then you might get the same vector back. But whereas if you take the curve and you transport it up to the pole, transport it down, and then transport it back, you would not get the same vector back. So how your vectors parallel transported is dependent on the curve. Okay, and what we can do is we can use this to define an intrinsic definition of curvature. So let's just have a look at this. The thing that we use to describe, just the name basically, the thing that we use to describe curvature is this tensor. It's the Riemann tensor, and it literally encompasses the fact that both the path dependence of curvature, and eventually it shrinks that path to an infinitesimal path, and it actually stores how your manifold is curved. And after the metric, this is the most important tensor on the manifold. The metric gives you an idea of how you make measurements. The curvature tensor gives you an idea of actually the shape or the structure of the manifold. And when we solve Einstein's equations, what we are solving for is the equations we write down, the second order equations we write down, restrict parts of the curvature from the mass. And then we solve those secondary order equations to give us the metrics. They're secondary equations in the metric, and then they are like Newton's generalized law that then relates the mass or the content of the space-time to actually how it's bent. And then we solve those second order equations, you get the metric. Once you've got the metric, you can study what you guys are doing and studying the geodesics in that metric. But the basic structure of space-time is coupling the curvature to the matter. Okay, so I've just given, it's basically we have a 4-index entity, that's the curvature, which we're going to actually get now. Always associated with curvature is the failure of successive differentiation operators. So the fact that your differentiate operators, if you're not applying them to a scalar, don't commute. In other words, you can't swap their order. That is always related to a curved manifold. If the manifold is flat, you can change the order usually, but if you can't, then you do have a curved manifold. And we'll see how that works as well and write down the equations that actually quantify that. Okay. We're basically going to go and we're going to start here and work out the consequences of the idea, and then we're going to use it to define the Riemann tensor. Okay. And then what we're going to show is that this tensor, even though curvature or the mismatch in parallel transport may depend on the path, The curvature tensor doesn't. So in other words, the curvature tensor is once again a tensor that you can get, a 4-index quantity that you can get at a specific point that encompasses all the curvature, and then we no longer have to use this fact that our vector being transported may depend on a path. So it's another way of losing the path dependence, is to put all the information we want to find about the curvature in the curvature tensor itself. Okay. And so basically when you have the failure of a vector to parallel transport along a closed curve and return to itself, you basically have your curvature tensor, and this failure is actually going to be much easier to calculate when we actually have the Riemann tensor itself.
So is the failure then not saying it's not a geodesic?
No, you can look, you have two things. Geodesics are paths.
Mm-hmm.
Okay, so a geodesic is the curve itself. Parallel transport is any closed curve on the manifold. So you have the set of all possible curves on your manifold that you can, or closed loops on the manifold, and you can parallel transport along that, and then you'll have a mismatch in the vector when it returns if it's a curved manifold. If you choose a different loop, you might have a different mismatch. Okay, so those are curves. What you are transporting is a vector. Okay, a geodesic is a specific type of curve where its tangent vector is parallel transport with respect to itself. Okay, so it's a very special set of curves in your manifold.
Yeah.
It is true that your geodesics also sweep out the curvature. By watching the geodesics, you can determine what the curvature is. And in fact, that's what we want to do when we test GR, is we want to look at what an object moving on a geodesic, and then we want to attribute that motion we want to attribute what we see to the curvature content of the space-time. That is like the holy grail. If you can do that well, then you've solved many problems. It's a very big open problem. Was how you directly determine your manifold simply by watching geodesic motion. In principle, mathematically, I believe it's solvable. Nobody's done it yet. Okay, and that's actually how my interest in the bumpy black holes and testing GR and your problem started. Was actually watching a motion of a geodesic, can you determine the curvature exactly? There are some people that made a plausibility argument. The guy's name is Finton Ryan, that said if you watch an object orbiting another one for long enough, you should be able to reconstruct its basically space-time or curvature structure. But how to do that practically, nobody yet has. And that's one of the main ways we're actually going to test GR. Okay, so the Riemann tensor, if you start with a derivative operator and you start with a dual vector field, okay, and f is a smooth function. So what you want to do is you want to explore the effect of two derivative operators on f of omega c. Okay, so remember when we worked out the curvature, when we started defining our Christoffel symbols, we looked what happens if you switch. We worked out the difference of two gradient operators. We worked out the application of two different gradient operators or derivative operators to f of omega c. Okay, so what we're going to do now, instead of just looking at the application of one, we're going to apply two derivative operators to f of omega c. Okay, so what we're going to do is apply this, and then what we do is simply use the Leibniz's rule, and we apply with the first operator. So we have the gradient of A times the gradient of B. F of omega c is equals to the gradient of A, which we still have to do omega c, the gradient of B of f, plus f times the derivative operator of B applied to omega c. And we then apply this one, and once you again use the Leibniz's rule, so we're going to have omega c gradient A gradient B of f plus the gradient A applied there times omega c times the gradient B of f plus the same thing to those two. Okay, and what we can then do is simplify this a little bit further. Okay, and similarly we can do and look at what happens. So we can't yet, no, you can't simplify that further. What we can do now is look at what happens if we switch the two. Remember, the order is important. Okay, you can't just switch the two. So let's work out what this thing is, and you can get it exactly from here just by switching A and B. And then we can go about and we can say, let us now subtract the two from each other. And then all the light colored terms basically cancel. So you have this gradient B omega C cancelling out. So those two cancel out. And you're going to have this gradient B of F omega A of S. Those two cancel out. And what you're left with is basically this difference is then equals to these terms with just F. So it's F times the differences in the two operators applied just to omega C. And that's basically it. Okay, so you have okay, minus that. So this one, the gradient of F times the gradient of B applied to omega C is equals to that one. Okay, so those two just subtract. And you've got basically this, the gradient A of omega C, the gradient F, so that one goes out. Okay, and then you have omega C gradient A gradient B of F minus omega C gradient B gradient A of S, F. But your definition, one of your axioms for your derivative operator was, remember that if you apply the derivative operator to a scalar, then it commutes. Yeah. Okay, so I think that was C4 or C5. Anyway, so these two cancel out because of your definition of your derivative operator, and then all you're left with is F times the difference between these two guys. Okay, so this is very, very similar to the case of different derivative operators. And remember that argument, the moment you had something like this, you could then argue that the difference in derivative operators depended just on the point and not on the vector field away from the point. And the same thing you can do over here. Because you have this expression where if you apply the difference in the two derivative operator of a scalar field times omega C, and that's equals to simply the scalar factor taken out, you have that this thing is a tensor, okay, at point P, and it depends only on values of omega C at P, not the way you change it off. Okay, so as a result, this guy defines a linear map, and from the dual vectors, which is omega at P, like omega C, to a type 0,3 tensor at P. Okay, so you get the fact that it's a linear map just from the fact that it doesn't depend on WC away from P. And the fact that it's a 0,3 tensor, you simply get by counting the indexes that it's actually working on. Okay, so what it does is it basically goes and it behaves like a 1,3 tensor. Okay, so this immediately means there exists a tensor field that we call this, which is our Riemann tensor, A, B, C to D. And it basically exists for all due vectors omega C, and such that this difference in derivative operators applied to omega C is equals to the Riemann tensor applied to contracted with omega D. Okay, so it's literally saying that when your derivative operators aren't equals to each other, or when they don't commute, their failure to commute is encompassed in this tensor. It's dependent only on the point, the value of the the one form at the particular point, and it's all the failure to actually be equal is hidden in this tensor. And you know simply by counting indexes, there have got to be 3 indexes below and 1 to contract with, and that's it. Okay. And so what you've basically shown is the existence of this tensor. Okay, and what we're going to do next is look at all its properties. Okay, so this is simply one way of defining this Riemann tensor. Okay, so the tensor field RABCD is called the Riemann curvature tensor, and it has many nice things. Okay, so the next thing is to actually see what this thing means physically. So let's consider a case where you start at a point P, you parallel transported a small distance, delta S, in one direction. Then you parallel transported another small distance, delta T, in another direction. And then you parallel transported back minus delta S and then minus delta T back to the point that you started. Okay, so basically, let S be a 2D surface in a manifold, let P lie in S and choose coordinates S and T, such that at point P you're actually at the origin, and then consider a tiny closed loop in this manifold. And what I'm basically going to do is going to prove to you that the failure to return to itself can be actually written in terms of the Riemann tensor when you shrink the loop to an infinitely small loop. Okay, so we basically move delta T along S equals to 0, then delta S along T equals to delta T, then back delta T along S equals to delta S, and then finally back delta S along T equals to 0. So it's this basically infinitesimal loop that you're working out. And we want to compute the change of vector A, VA, just in general, as the loop is traversed. Okay. So the thing is to find the change in the scalar VA, the contraction of the scalar VA with omega A. Okay, for an arbitrary vector field omega A. So you literally want to work out the component or the change in this dot product, but you're going to do it for any vector omega, basically for any and for all vectors omega A. Okay, and so what you do is for small delta T, the change delta 1 for this first part, okay, is simply delta T times ddt times this thing evaluated in the middle over there. Okay. And it's simply a better approximation at a point. And then this, and it's basically accurate to second order in delta T. Okay, and so the way we do it is let TB be tangent to the curve of constant S. In other words, TB points in basically in this direction. So TB points along that curve. Okay, and let VA be parallel transported along TB. So we're going to use this parallel transport condition to try and work out how this inner product actually changes. Okay, so we're going to have delta 1 equals to delta T times TB. It's basically your parallel transport condition applied to the dot product. Okay, and to apply it to the dot product, we have delta T times VA, TB gradient of omega A evaluated halfway along the curve. Okay, and what we can do is simply work out the same thing for the change over there, and the change over there, and the change over there, and then add them all together. Okay, So this change over there, I'm first going to add to that change. So I'm going to get delta T times VA TB, the parallel transport operator applied to omega A, evaluated halfway between the 2 points. And then I'm going to get minus this guy, because it's going the other way, evaluated over there. In other words, delta T over 2 delta S. And then I'm going to do the same thing for the changes over here and the changes over there. Okay. And what's going to happen is that to first order in delta T and delta S, I'm going to then be able to sum this guy and that guy together, and I'm going to find the total change in delta V dot omega A. And because this omega A was arbitrary, I'm basically going to get the total change in VA. Okay. So what basically happens is the parallel transport is path independent to first order in delta T and delta S. Okay, so if delta T and delta S is small, then it's independent of the path. Okay. If the path gets large, it's not. It depends on the path. But when these guys get small, it's independent on the path. And the moment it becomes independent on the path, we have an entity at a point. Okay, and that entity we're going to show is exactly related to the Riemann tensor. Do you have a question?
What do you consider as small?
Limit as epsilon goes to 0. In other words, it's the same. It's basically, what we're basically doing is we're working out a derivative operator on a unit ball. It's like tiny. It's like unit ball is order 1, right? Yeah. So as epsilon goes to 0, much smaller than 1. In other words, you're literally taking a loop and you're shrinking it into a point. Yeah. And when you get to the point, you find, at least in linear order, these changes in the dot product vanish. Okay. Yeah.
Another question. So if we were to change the direction, so if we went clockwise and now we go anti-clockwise on the same curve, are we going to get the same result?
No. Look, if you parallel, you're not going to get the same result. If you parallel transport this vector that way around, you're going to get a different vector. Okay? So if you were to take that vector and then transport it that way around, it's going to point out. However, if you were to take the answer you got from the first parallel transported and reverse it, you would get back to where you started. Okay.
So it's irrelevant for how it changes, it's just the fact we want to see if it changes.
We want to see how much it changes.
Yeah, but I mean, how much that side will be the same if you go that way around or that way around.
Yes, I think, the difference would be.
At the end, basically the difference will be the same also.
Yeah, the difference will be path. Yeah. The difference is dependent on the path, but only at quadratic order in delta T and delta S. Okay, linear order, the difference doesn't depend on the path at all. Okay. Okay, so that's the change in the first bracket. Okay, so what we're going to do now is we've got the first order change. We now want to compute the second order change in the bracket. Okay, so delta 1 plus delta 3 is simply delta T times this guy minus that guy. Okay, and we want to evaluate it at T equals to delta T and a half equals to a half. And so what we're going to do is parallel transport VA and T delta V VA along the curve from delta T over 2, 0 to delta T over 2 delta S. Okay, so delta T over 2, T0 is there, and we're going to parallel transport it along there. Okay, and in first order in delta S, VA at delta T over 2 delta S, in other words there, is equals to the parallel transport of VA at delta T over 2A. So it's equals to that guy, okay? Since it's the parallel transport is independent of first order things. But, okay, this term at delta T over 2 delta S will differ from the parallel transport, okay? So these two terms, VA is the same, but this guy over here is different whether you evaluate it over there or whether you evaluate it over there. Okay. And the amount that it is different is simply delta S, which is the change in S from here to here, times S of C contracted with a gradient C TA delta S omega A. Okay, and where S of C is the tangent to the curves at constant T. So S of C is tangent over there and over there. Okay, and the term basically is just this quantity contracted with VA. Okay, so in second order in delta T and delta S, what you then have is that this change in path is equal to delta T delta S VA, the tangent to the constant S curves contracted with the parallel, basically the parallel transport along the S curves contracted with a parallel transport along the T curve of omega A. And you have a similar condition for omega or delta 2 and delta 4. What you're going to have is that difference, that total change in the contraction with an arbitrary vector is also going to be very similar to that guy. And you're going to actually add it together, and then you get the total change is simply delta T delta S, your vector VA, with these two, the difference of these two guys. Okay, so on an infinitesimal level, the change of this thing is second order in delta T and delta S, and the change is given by this expression. And if you look very carefully at this expression, you can actually go about and you can simplify it, and you can see you're eventually going to get the difference of two derivative operators applied to WA, and you can use your definition of your metric tensor to get what that is. Okay, so if you have a coordinate vectors, in other words, they commute because they are derivatives of a scalar function, okay, then what you're going to be left with is TCS of B with this derivative operator applied to omega A, or omega A. Okay, and then you're going to have that this difference is simply, by definition, that we found our Riemann tensor over there. And so what you've basically proven is that if you shrink the path you're taking to an F very, very small, the dominant change in the path occurs at second order, and that change in the path is directly related by the Riemann tensor itself. So to measure the curvature of a manifold, you simply have to see how derivative operators fail to commute around a closed curve. And that is basically kept in your Riemann tensor. Okay. And so since this argument holds for all omega A, if and only if the change in the vector around the path is equals to this thing. Okay, so what you've done basically is connected an infinite change in a vector around a closed path with a Riemann tensor. And so, to the earlier discussion, the change in the two vectors doesn't depend on the path, if the path is small enough, and it depends only on the point, and all that information of the change is kept in the Riemann tensor. And for a specific vector, you can get the change simply by contracting that vector with a Riemann tensor. Okay, and so what you're basically going to have, the Riemann tensor basically directly measures the path difference of parallel transport. Okay, so just by cleverly manipulating the exchange of derivative operators onto this one form, you can basically show that if you parallel transport this vector, its change is independent on the path at lowest order, and it's given just by the Riemann tensor. Okay, so the next thing is to study that thing more generally. So we looked at the commutator of a derivative on a covector or a one-form field, just like we did with the Christoffel symbols, where we switched it over and we worked out the derivative operator on your vector field, and we got it from what the derivative operator does on the covector field. We can do the same thing here. So what we can then do is basically, if we use property 5 of the derivative operators and Leibniz, we can also work out that because we're applying the commutator of derivatives to a scalar, that must be 0. But we can then expand this thing out, okay, and then expand it out again. And what we can go is we can use our definition of our Riemann tensor that comes in over here to work out what the definition of this commutator is to a particular tensor field or vector field. And so we can simply replace our definition of our Riemann tensor as the commutator of the derivative operator applied to the one form over there, and therefore get what the commutator of the derivative operator applied to the vector field is from that. And since it must hold for all omega c, we can change this thing into omega c simply by relabeling those indexes or switching c and d, because it's just a dummy index that we sum over. And we can get that the difference in derivative operators applied to your field over here, your vector field is simply minus t times d of t, or sorry, t, the dth component of t contracted with your Riemann tensor's third index. Okay, so we now have a way of storing all the commutators of derivative operators in a curved manifold in terms of the Riemann tensor. And so it actually allows us to switch the order of derivatives provided you add in a term that contains your Riemann tensor. And your Riemann tensor, if you know the metric, is known. Okay, and then in general, you can also do this to any tensor. Okay, and you do it basically, apply the rule for sort of vector indexes. You add a minus TD or component contracted with the third index of your Riemann tensor. And for one form indexes, you actually add the other expression that we got for the one form. And so what we have is over here, where we have our vector indexes, we contracted with the third index over there. And where we have the one form indexes, we have a plus. And we choose the one form index, for example, E, and we contracted with the fourth index of the Riemann tensor. Okay, so once you have your metric, or once you have your Riemann tensor, you can always switch the order of differentiation. Okay, and it's dependent only at the point. Right. So Riemann tensor, allows you to switch to order differentiation. It measures the failure of a loop to parallel transport and how the vector changes. And there we're going to stop for now because you have to go. Okay.